Okay, good morning. We have a far smaller class, right? Um, so first thing, the exam would be after the spring break, right? So you have either of three options if you want a fourth one, sure, right? I won't be there on Monday. So essentially I have some envelopes, so if you want a hard copy that you want to take it and then take it at your leisure, that's fine. If you want it to be sent by email, that's fine. If you want to come to class and do it, that's fine too, right? I won't be back till Wednesday night, so I won't get a chance to give it back till Friday, right? And the exam is a little different. It's multiple choice. I'll give 7. You get the best of 6, right? So, but the other way, it's still +1 for right, -1 for wrong, and so with the multiple choice. So if one answer subsumes another answer, so if you have a question where the answer was A, B, A and B, A or B kind of stuff, right? So if you answer just A, you don't get any credit. If the answer was A and B, you need to give the correct answer, right? The multiple choice thing. So however you want to take it, let me know. Right? Does that make sense? Yeah.
When you say you don't get any credit, do you mean you get 0 points or -points?
0 points. Oh, -points, sorry. So if the answer is A, B, A and B, A or B, right? If the correct answer was this, you cannot answer this, right? Looks like it's going to explode. Right? Yeah, so this is wrong answer, right? So you cannot argue that this is subsumed by this answer because it's right. Okay. So there are a lot of questions about the home program. So there should be a handout going around today, which adds to what we had last class. So if you didn't pick up the last class one, I have still some left, right? So there are a lot of questions about what you mean by read from a page, write from a page, and many of you may have gotten it right. Many of you may not have gotten it right. So I figured I'll go through them. I think I went through them in the email and text. It doesn't quite work when you have to convert everything to ASCII text, right? So I kind of tweaked a little bit of about the addresses I sent out in the email, right? So assume this is your pin trace. We don't worry about the first part, which is basically the instructions, and we don't worry about that, right? Even though it will cost its own set of page faults and all those things. We only worry about this component, right? So it essentially says that you accessed something in in logical address space 8190, and you read something there. You wrote something in 8191, you read something from 500, and you read something from 8192, and then you read something from 200, right? So if you assume an 8K page, this is, in the logical address space, the page number is 00010, right? So that's your reference string that we went through in class. So essentially you do 00010. This is the reference string that you're trying to operate with. And of those, this is read, this is write, this is read, this is read. Yeah, the rest of them are read, right? And for this, you need two pages, right? That as the maximum. So if you have 2 pages, then you won't have to evict any page. So we take let's look at the case where you have half of those, which would be 1, right? So your page logical address page table would have 2 entries. Your physical address space is 1, right? So when you start out, these entries are invalid, right? And that's what I meant by the invalid in the email, not setting the invalid bit, right? So I'm not going to talk about what hardware would impose. I'm only talking about the logical notion of what happens. So when you start out, whatever is in here makes no sense. You just leave them, right? So the first page, first this happens, right? You try to read 8190. So you look at this page, it's invalid, so you get a page fault. Your page fault count now becomes 1, right? So you need to read the page. You assume this somewhere here. So you read a page from here to fill this physical page. So your read count goes to 1, right? And then you set this page to this address to point to here, and the OS gives control back, right? And then the next instruction happens, right? So it modifies something in the page, so you could keep track that this page was modified somehow. You keep track this is modified. Then you see another read. You don't have to do anything because the page was modified, but nothing else happened. Then you see page 1, right? So at that time, you're trying to access this entry. So it's invalid, right? So you notice that there's only one page left. So your replacement policy for the simple case, whichever one you use would have to replace that page, right? So essentially your LRU and all those things come at this point of trying to figure out which one has to be replaced. And it's a trivial example. So you choose this one. So when you choose this one, since the page was modified, you would have to write this somewhere, right? So your write count will go to 1, right? And then you read whatever should go here from disk, right? So your read count will now go to 2, and your page fault would have been 2 because you got a page fault while you're doing all this stuff, right? And at this point, you set this to null, and then this points to here, right? So when you go to the next instruction, it's again not in the memory, but it was not modified, so you can just throw that page. So you read the previous version of page 0 in. So your read count goes to 3, the page fault count goes to 3, and that's where you end, right? So essentially your read count happens to be 3, write count happens to be 1, and page fault happens to be 3, right? Yes?
Is there any scenario where the page fault isn't going to be the same as the disk reads?
If you assume, if you write that the first time you read the page, the page doesn't have to be read from anything, right? Then it'll be different. If you assume that the first time I said, when you come to this, you read something from the disk, right? You could have assumed that the page, because the program just started, so there's nothing really from the disk. If you assume that, then it'll be different. But otherwise, it'll be the same. Yes.
At the end, at the end of whatever program you're doing, if you have a couple of pages that have been modified, do you have to just then write all those back?
You probably should. Yeah. So at the end, if this was right, you would write it back. Right? So that's what I meant by what happens, right? So the simulator, it's not really that complicated, right? If it looks very complicated to you, then that's not the intention. So this is essentially I want you to run through this reference string that we discussed in class and see what would happen in a real memory, right? So all the real addresses, all the 32-bit addresses essentially translate to this reference string. We did this in class like this, and this is what you're trying to implement. And for doing this, if you have to keep a data structure here, which is write, read, whatever, that's fine. In a real machine, you're forced to deal with whatever the hardware gives you. So if the hardware gives you reference bits, modify bits, then you're forced to do that. And you could do something like that. You could do whatever you want. But all I want is for you to capture this, not how you implement this, right? So when I think in the email, when I said invalid, I didn't mean the invalid bit in some of the hardware. I just meant that this address is not valid. You will get a page fault, right? Yes.
Why? There's 2 memory frames there, right? In this example.
This is a logical address space.
Right, and you're using 2 of them, right?
Yes.
So why did you have to take the first one out of memory when you read it in the second page? If isn't there room for 2 different logical pages in the page?
There's room for 2
right.
logic. So actually, the logical address space could be longer, right? We don't really care because all of them are invalid, right? But I said you are only allowed to have half of the number of pages that you touch, right? The number of pages you touch here is 2, so half here. So I'm forcing you to leave this as 2. If you have, one of the cases you do is 1/4, half, 3/4, and 1, right? Quarter and 3/4 don't really make sense when you have 2. So assuming that you have 2, right? Right. So what would happen in that case, right? Yes.
Well, it would be the same thing for the first step, right? You have to read it in.
Yeah, read count is 1, page fault is 1, right? And when you hit here, right, you get a page fault, and you can assume you get a read count, right? And so you can you might have left it like this, or like you pointed out, when the program ends, you write out the last page, the modified page, right? So your modified page would be 1.
But you would only write when it needs to be kicked back out and replaced, right?
Yes.
Okay.
But in the case when if the program exits at this point, you would want to clear out all the pages, right? So at this point in this program, right, however many instructions there are, it doesn't really matter, right? You will only have 2 read counts and 2 page faults. That's it.
And that's all.
Up to two writes.
And that's all we need to get out of our simulator is just number of read counts, write counts, and page faults.
And then draw a graph. So you're drawing a graph where it says that 1/4, half, and 3/4, and 1, and for the different ones, right? So for the 3, and for the write, and for the page fault, and so you would have to run the experiment many times, right? So you'll run it for quarter, half, 3/4, 1, LRU, all the different algorithms, right? So there are a lot of combinations of things you would run, but your program itself should not be complicated. You'll have to run it many times to get the graph and plot them and all those things, right? Yes.
So you only consider read the first time you bring in that frame?
Yes.
In other words, that's-
Yes. So I'm worried about the read from the disk. I'm not worried about reading from the memory page.
Okay.
So once it's read into the memory page, you can read as long as you want.
And if it times out, increment it.
Yes. So for example, in this case, when the page when the multiplier is 1, you cannot get more page faults than the number of physical pages. Yes.
And if you brought in a page and you only read it and then needed to kick it back out, that wouldn't affect your write count, right? Because
Yes.
it hasn't been modified.
Yes. Yes.
If you come to like a write in the trace and it's not in the page table, you have to read it in first, right?
Yeah. So you'll get a page fault, you bring it in, then so when you see a write in the trace, you actually don't write anything, right? So at this point, you don't really care about this. You only see this part, you get a page fault, you bring it in, but you keep track somewhere that this page was modified, right? The actual write only happens when you try to kick out the page, not when the trace says write, right? The trace write only triggers some flag, not actually change anything. Nothing goes to the disk, right? Does that make sense? Right. So it's no complicated than that. So you don't have to make a lot of anything more complicated. So for example, I think one of the things we talked about last class was you may push the pages out to the hard disk if you're idle and all those things. Don't have to do any of those, right? So that's that. And if you have any more questions, I think talk to me, because I think it's in the email. My notation was very confusing. Yes.
There's one more question. So you want a graph for the read count, write count, and the page fault. Just have a graph for each of them for every simulator we run, right?
For every trace,
Right.
you could draw the LRU and all those things in the same graph.
Okay.
I mean, so you could let's say you have like something like this, right? You could say LRU, the different policies can go in the same graph, but you will have different graphs for different traces.
Mhm.
Right? So there'll be 9 graphs, right? 3 different traces, and for each trace there are 3 different replacement policies. And for each one of them, there'll be 3 different lines. Right? So this is probably a good time to have a shell script kind of thing to repeat those experiments rather than doing them manually. Right? Is this what people assumed, or something slightly different, something really different? Right? Hopefully this will solve the questions. I'll be here all spring break. I'm not leaving till next Saturday. So, I think it probably may be better to drop by if you want something, because I don't know how to explain this in linear form, right? I mean, it's easier to just point arrows and stuff, right? So, while I was discussing this, right, I think this is relevant to what we're trying to do, even though it's kind of sort of related, right? So you might have run into this segmentation problem with C programs, right? Segmentation fault, you get segmentation fault somewhere, and most likely you get segmentation fault inside your printf or scanf or something. And the first thing, whenever you learn programming in C, the first complaint that I've seen students have is, my C compiler is broken because I'm getting a segmentation fault inside scanf, right? It's not even my code, so why am I trying to debug this, right? You might have said that, or you might have heard that often, right? So here's a simple piece of code, right? It may work out because you're lucky. Essentially, I'm just declaring a variable. I'm not initializing it to anything, right? So let's assume that it gets filled up with something randomly. I mean, you try to write into that pointer. You get segmentation fault sometimes. You don't get segmentation fault some other time, right? And some other time you get segmentation fault way off somewhere else. It seems like it's a programming language issue, but it's actually related to what we are trying to talk in terms of page replacements and stuff. Anybody wants to make a guess of why we don't see a page fault at this location all the time? And why it seemingly happens inside a printf? Yeah. A scanf, sorry.
Because sometimes that's going to be a memory address that the program has access to, and sometimes it won't be.
Mm-hmm. Let's say you have another pointer somewhere, right? I mean, I'm just making it easy, but it's completely non-deterministic, right? So this pointer may happily point to the same location that this was, right? Because it's random, so it could be pointing to anything. So there are 2 cases. One is it's pointing to something that you already have. It's pointing to something that you don't have, right? If it's pointing to something that you already have, you doing this is really modifying this, right? So next time you try to use buff, the buff will not have what you expected, right? So in your piece of code, if you say, buff equals, you should do a string copy. Let's assume this for now, right? And then you do this, and then you do a printf of buff, right? In this, don't worry about too much about the exact syntax of the stuff, right? So my point is, if pointer happens to be pointing to what buff was, buff might have been overwritten by this 10, right? Which no longer is null terminated. So you run through the memory, you print some stuff, and then your program will crash here, right? So if you're really unlucky, this can go on for a long time and it come back to you after a long time. If you're really lucky, you can catch it right away, right? Sorry. So depending on, hang on, let me. So depending on where you set this up, right? You may end up with something, right? And sometimes you may not code up at all, right? If you never use this buff after this point, then you are lucky and your program will work fine, right? And it points to something else that we concerned about, which is if this pointer points to something that is not in your address space at all, then you will try to go to the logical page. You'll get a fault to the operating system. Operating system tries to, look up the page, and notices it's not part of your address space, so it kicks you out, right? And then you get a segmentation fault. But if it's not something that OS will get involved, if it's not in a page that it does not belong to you, OS would not get involved, so segmentation fault in that case cannot be caught, right? It goes to the same thing that we were concerned about before. OS does not get control all the time. OS only gets control when you access a page which is not in memory that a page fault should happen. So if you are lucky and you mess up your own program, you can happily do that. And when you do that, you may fail. You may fail in strange ways. You may not fail at all, right? You may not fail at all doesn't mean that your program is working right. You may have changed some variables that you don't notice. So somewhere in the string, suddenly you notice that you're printing something, some output. You have some strange magical stuff happening from somewhere to here. And I'm sure some of you have seen that, right? So that's the reason why segmentation faults are so frustrating, because it's not, it touches on something that we see all the time, we're talking about. Unless you touch something that the OS should get involved, OS has no way of knowing whether you're doing something which you're supposed to do or not supposed to do. And OS only cares to protect you from touching somebody else's code. OS does not really care if you write a bad code. OS does not really care if you start writing into your code, do all kind of weird things, right? So you may land up in a point where you just walk through your code, crash your code and all those things, but you may sometimes do this stuff, right? And there are, for people who are very, very good at C program, there are a lot of strange ways by which errors can happen and stuff like that, right? One of the strangest things you can happen is the way malloc call works, right? Malloc, how many of you understand how memory allocation malloc works in detail? So the way malloc works is it asks the operating system for a big chunk of memory, right? It uses a system called SBRK, sbreak, right? And gets a big chunk, right? And then your library gives out some little bits of memory to you for you to use. So when you do free and all those things, it gives you memory and then takes it back, right? And so it has to keep track of all the things we talked about, fragmentation, internal fragmentation, all those things. It wants to make sure that it gives out the right set of addresses to you. So it will have to say your request, let's assume you did a memory allocation for these two chunks, right? And these are free. So it has to keep track of what is free and what is not free in order to do its allocation, right? That's what the call will do. If it cannot find any free space at all, you'll do sbreak to get a larger chunk and start handing out to you, right? So to maintain this list of what is allocated and what is not allocated, it maintains it as a linked list, right? The way it maintains it as linked list is on the next byte after this, right? It stores the address of where the next one is allocated, where the next allocation happens, right? So you can go through this to figure out all the stuff which are allocated. So when you do a free, right, it'll go through and see the address which is right next to what was allocated to you, and then use that to move the pointer so it can reclaim this space, right? So what could go wrong if you have this stuff? But if you do it like this, what could your program do which will mess this whole thing up? Right? Let's say you ask for 10 bytes, right? So it'll give you 10 bytes. On the 11th byte, there's an address which points to the next allocated malloc buffer, right? It's not really related to what we are talking about, but this all affects you, and it has an implication of what things happen, right? Yes?
You could write something to the element byte.
Yeah, so if you don't do a bounce check, and which is people casually do, right? If you do a read line or something and you read 11 bytes, for example, you're not supposed to do it, right? But you won't get a segmentation fault because it's all part of your memory space. So you write into this and you write into this pointer. So now this pointer is no longer valid. So you won't notice it till you try to do a free. If you do a free, then this free tries to look at this address and it's pointing to something else, and all strange stuff happens. So this you'll usually notice when you get a code dump on free, right? And I don't know how many of you have seen that, and first instinct is to say malloc is broken, right? Because I tried to do a free, I got this address, I'm doing a free. You can do a print to see what was allocated to you, and you can do a print to see what you're trying to free. They'll both be the same, but malloc free will fail, right? It's failing because this pointer, you ran over it, right? And the reason why it does that is this is a quick way to find out that you actually messed up, right? So malloc people do not consider this as a problem, because the next time you do a free, you'll get a page fault, so you can fix your code. So they don't want to fix it by making any other pointers, but many of you may have seen so there are a lot of things that C does in terms of segmentation faults and stuff are artifacts of how this memory allocation and all those things happen, right? Now, of course, there are smarter memory allocators which do some checking and stuff, and that's not the scope of this class, right? So, little digression. So let's get back to the task at hand. So, do you have any other questions about how this paging and all works? There are some loose ends that I would like to kind of finish up. They're not loose ends. There are other aspects that really matter. One of them is the working set, right? So we left off at this point when we are trying to figure out how many frames should go to a different process. So in the graph I was talking about, you just got how many frames that you wanted. There's no question, because there's only one process. Even in your memory simulator, you have only one process. But real machines have many processes, so how do you give the allocation, right? So for that, the first notion is you need to have a notion of a minimum number of pages, right? And that's at least the number of pages that you need for instructions to run. So if your instructions always require at least 2 pages, right? So for example, in the case of here, I said let's not worry about the instructions, right? If I did worry about the instructions, then this needs at least 2 pages. One for the data and one for the instruction. So in this case, if I only had 1 page, nothing will happen. I'll get a page fault, get the data in, then I get a page fault, bring the instruction in, then I get the page fault, to infinity. So depending on the particular machine, you may have to have a minimum number of frames given to a process. And it's usually very small, so most modern machines you tend to give that. The maximum that you want to give, you can either do it fixed or priority-based schemes. So in the fixed scheme, right, you can either think of allocating how much pages you have, physical memory you have, equally among all processes, or proportional to the size, proportional to how much size you want. So the little equations to essentially say that, I can say there are 10 pages, I have 1 gig, so I'll give you 1/10 of a gig to each process, right? Or I can give processes which tend to be large more memory than processes which tend to be small, based on notion of how many pages that they might want, right? And you can also think of a priority allocation, right, where a process with a higher priority would get more memory pages. A process with a lower priority would get less memory pages. What that means is that the replacement algorithm would take pages only from a lower priority process and not from a higher priority process, right? So these are different ways how you could balance what a process wants with what the global system does, right? And the replacement may also be, so you can either assume that once allocation is done to a process, the process sticks with it, or the process can request more pages. So with the local replacement, once a process is given, say, 10 frames, it's not allowed to ask for more, right? It's not. You don't take away the 10 frames that it has. You don't give it more. So in one sense, it's good because it has whatever it needs and it keeps running, right? But it can't make use of other processes being finished and then more memory being allowed. In the global replacement policy, it can do a good job of trying to balance what is left for a number of processes. So when you start the program, if you have 10 processes and I gave you 1/10 of the memory, right? And after a while, half of them leave and only 5 processes. Then with the global replacement, your applications can now have 2/10 of the memory, right? And it's good in that sense, but the complication is now you have to make sure that you get the right number of pages from the right set of processes and stuff, right? The other issue is if a new process comes in, it has to slowly start getting it. Whereas in the if I do a static allocation, the new process comes in, it'll have free space left by other processes, right? So those are different ways of doing the stuff, and operating systems do different things, trying to balance what each process wants with what the overall system should do, right? So this brings up two issues of performance. So the reason why you're doing all this stuff is you're trying to bring stuff from the hard disk and trying to make programs virtually assume that they have more memory than what is physically available, so you can run different programs, right? But there's only a limit of how far you can go, right? Essentially, the limit is something like what you're seeing here, right? It's a very small example, but if you have just one page and you have two processes, and suppose the reference string was 0, 1, 0, 1, 0, 1, like this, right? And suppose you have only one physical frame, right? A reference string like this would be horrible because every instruction would cause a page fault. Every instruction would mean that you need to read something. So yes, you will in fact make these two programs run, but they will run at a very horrible pace, right? Horrible pace basically decided by what the hard disk is doing. So how much the hard disk, essentially the bottleneck is the hard disk. You'll try to bring the pages in, you do a little bit, then you bring the next page in, you do a little bit, then you bring the next page in, a little bit, kind of stuff, right? And that is called thrashing. Many of you may have faced it. So back in the days when you had, when machines have very little memory, you would have faced it often, right? If you install, like, say, 64 meg on your Windows XP machine and say start PowerPoint and Word and something else, right? All these programs will run, right? All these programs will run in the literal sense, right? But practically, if you move the mouse, you might as well go for lunch and come back, right? Because everything would. So you'll see your disk go wild. How many of you have seen that behavior, right? So how much memory did you have? Do you remember?
Well, normally I have 384 megabytes, but one of my memory modules is broken or something, so it dropped in half.
Okay.
And Windows decided it didn't like it. So.
Yeah, I think Windows won't. I'm not exactly sure how much it absolutely minimum it needs, right? I think it's like they used to say it's something horrible like 4 megs or 16 megs or something, right? That number means that yes, with 4 megs, the system will eventually do something for you. Or system, you can, theoretically it can do something, but practically cannot do anything because you do anything, you move your mouse, then your disk will go wild. You can't do anything else. You can't interrupt it or anything because it's trying to bring the pages in, right? You cannot interrupt a process when it's trying to bring the pages in because it has to get the page in and restart that particular instruction before you can give control for you to do something else, right? So your machine is practically dead. So that's the notion of thrashing. So when the process is busy just swapping disk pages in and out, it's called thrashing. And usually it happens when the amount of memory is small, right? And we'll refine that to mean what that small is, right? And obviously 4 meg is very small, but it's actually a little bit more detailed than that. And so one of the things which happen with this is your CPU utilization tends to go down, right? So how would you solve? How can you think of solving this problem of thrashing, right? You're basically bringing all these stuff in. What are some of the ways that you can improve this problem? Right. So would bringing a faster disk help? Yes. So we're bringing a faster processor help. So what would happen when you bring a faster processor?
Utilization would drop, and the OS might even try to bring more stuff into.
Yes, if you build a faster processor, your utilization will actually drop, right? Because you bring a faster processor, it'll finish whatever little work it can do sooner, and it'll wait longer for the hard disk, right? So one way is to increase the make the disk run faster. The other way is to not run so many applications, right? Because otherwise, the OS will look at the CPU and say, CPU is basically idle, so I can bring in a new process, right? And as you bring in more process, the CPU utilization keeps dropping. And essentially, sort of, you see some graph like this, right? As you increase the multiprogramming, as you cross this point when it starts to thrash, right? You can add more processors, and your CPU utilization continues to drop, right? And so you don't want to go into that region. You want to be before that point, right? And so the real reason how these things work is built on the notion of why demand paging works, right? The reason demand paging, the reason why we can do all this stuff is you expect a notion of locality, right? You expect that programs do something like this, right? If you only had one page, right? So the idea here is you expect that once I bring some page from the hard disk, I would reuse it often, right? And I would reuse it often because I'm doing something which makes the program behave certain way, right? So one of the examples is if you're going through a while loop like that, for loop like that, right? The instruction set, so the instruction part of that particular loop would sequence through back and forth. So while you're inside the for loop, the set of addresses would be sort of the same. So they're defined to be a locality, right? And we'll see a little bit later how it happens for data, right? Essentially, if you're going through an array, you tend to see that, right? So if you tend to go through a loop, if I can bring all the pages for that particular loop inside memory, then the OS does not have to get involved. So you can basically go through the stuff. If you have a program which goes in a straight line, right, then essentially you keep bringing pages. You'll use the page for however much you're striding through, and then you won't use it, right? If you have a program which is random, if you have a program which has lots of go-tos and stuff, it's keeping going on all over the place, then demand paging would perform horribly, right? So here is another reason why go-tos are bad and for loops are good, right? If you keep a for loop, then you expect that all these instructions will be reused. So if I can keep all the addresses, I need all the addresses for the instruction, for example, for that for loop in memory, then essentially the disk does not get involved, right? And so that's the notion of a locality. So you want to keep that locality. That locality defines what you can have. So here's a pictorial representation of what programs tend to go through, right? It's kind of hard to read, but essentially with time, right, the y-axis is the set of instructions that are being touched. And this is, you can plot this from the pin traces, right? So the bands you see here says that you're going through these set of addresses and those set of addresses. So when the program is running fine, you would have those in memory, right? And you also notice that it stays stable with time, right? So the same pattern stays there for a while, and then it kind of moves to a different pattern and so on. So as long as the pattern remains same, you have to bring in all those pages, and once they're there, you tend to use them for a while. So you assume pages do something like this. If all you see was a bunch of dots, right, all over the place, then that means you're basically randomly going through stuff, and all the demand paging would not give you benefit, right? And so that defines the notion of a working set. Working set basically says that if I can look in some time window, I can see how much traces are going through the same request over and over again, how many requests are being reused, and that defines the notion of a working set, right? So working set definition says how much I should look at. So depending on how far I look, I can get different working set, right? So suppose I would look at only one instruction, right? Then I would only look at just this little one. If I look at two, right, I would look at these two, and I don't see too much reuse. If I look at from here to here, I see these two pages are being reused a lot, right? So the working set kind of encompasses that. So working set basically says that from my time, like, look in the past to see how much of them was being reused, and I can get a sense of how many things are being reused. And it's a slide moving thing, right? So from the current time, I look to see how much the working space is. But as I move along, I should keep track of this window to try to figure out what are the set of addresses that are being reused, right? And we're doing this to figure out what does it mean for thrashing, right? So the idea here is, if the working set is larger than what your physical memory is, then you have thrashing, right? So if you look at this particular case, right, the working set for this would be 2, right? Because if you look from, like, say, from here to here is 2. So if you have one page, then essentially you are swapping that back and forth, you will thrash, right? So that's the notion of thing. So another reference thing there. So if you have a set of reference, and if you take say T1 or T2, and if you assume delta as the working set window, so from that, look back for that level, see how many unique pages are being accessed, and the working set was 1, 2, 5, 6, 7 to start with. At some other point, it's 3 and 4. So the working set keeps changing with time, right? So to keep track of that, it keeps changing with time. So you can't. So you need to kind of. You would like to reuse the value. So you like to say, whatever was in T1, when I move to T1 plus a little time, I would like to reuse whatever I calculated before, right? So the way you do that is you kind of split the time T into smaller chunks, right? And count how many accesses were made within the smaller chunk. So when you move to the next one, right, we reuse the previous one. So for example, if you had T as this whole thing, right, you split that into 3 little chunks, count, see what the working set for here is, and working set for here is, working set for here is. So when you want to go here, you can wrap off this and calculate the working set for this little one. Then you know that working set for this entire time window, right? That's one way of keeping the whole data in. And essentially that's what you do for here. So applications typically, whenever you get a clock timer input interrupt, right, you tend to calculate how much things there are and set those pages reference bit to be 0. So next time you come back, you count what pages were referenced, so you know what were part of your working set, and you use that to figure out what is referencing. So you can, for a 10,000 unit, you can either split it into half or smaller, right? And you have a trade-off. If you have lots of these little ones, then you have to do this often in the OS. If you have few of them, you don't have to do it often, but you don't have a good answer, right? So essentially, if you do this, then you can figure out when you're thrashing, because if your working set tends to be larger, you are thrashing. Most modern operating systems don't try to figure thrashing, right? What they try to do is they try to figure out what's the acceptable page fault rates, right? So you kind of figure out how much page faults are happening. If they're happening too much, then reduce your multi-programming. So basically stop some processes to let them finish, right? So you don't actually try to prevent thrashing. You try to tend to. So you try to see if you're doing too much thrashing, because you don't necessarily have to go towards thrashing, right? If your machine is kind of unusable, that's good enough. You don't have to fully go to thrashing where it's completely not useful, right? So those are the two other issues. So you just can't do this demand paging to the limit. You have to be concerned about how much you want to do, and that's defined by the working set. I'll go through a few pages. I'm going to go through them very briefly, right? So one of the notion is pre-paging, and we'll see that more when we go to the file system, right? So far we talked about bringing all these pages when we demand them, but we don't have to completely wait till they are demanded. You can do a pre-page, bring some pages in before they are needed, right? With the assumption that if you really wanted them, you can win, right? But if you didn't want them, you pay a penalty. So you try to predict what pages will be needed next, right? And I have one example to show how that might work. The other stuff is the page size. Depending on how big the page size is, you may have to bring in more pages or what have you. It causes fragmentation and things like that. And the last thing is the TLB reach. So essentially, you want to keep everything in cache. So you want all these addresses to be inside a TLB hit, right? So one way to do that is to increase the TLB size. So if your working set increases, you can increase the TLB size, which you really can't do, right? So the other way to do that is to make the page size larger. You kind of add 3 or 4 pages and treat them as one logical page with one TLB entry. But essentially, you want to make sure that your TLB matches your working set, because if it doesn't, then you'll get a lot of faults there, right? If your working set matches your TLB, that means all the memory could be potentially in memory, and your TLB can connect to all of them. So every address can actually happen in one clock cycle rather than something slower, right? So I think this is the last slide I have. The other stuff is how you program has a lot more implications on these than you realize, right? So when you use arrays are a good example of how they can benefit from all the stuff we talked about and how they can destroy all the things we talked about, right? Arrays basically are a string of numbers. I mean, it's a chunk of memory. So if you stride through them, right? If you go through them, typically you tend to do this for loop, right? You do a for loop, and then you go through these numbers and access each address points, right? So that's good if you do it the right way, right? So how many of you understand the row major implementation and column major implementation of arrays? You should have learned that in your programming class, right? So that essentially says that in a two-dimensional array, a programming language may decide to keep them row first or column first, right? So in C, so if you keep it at row first, that essentially means that row 1, row 2, like this, So you can say, let's say this is 0, 0, 0, 1, a certain way, or you can go the other way. So depending on how you do it and depending on how you stride, you could either cause every instruction to page fault, or you could do a good job, right? So the first example, every instruction would cause a page fault because you are going against how the addresses are laid out in memory. Whereas in the second one, you are exactly doing how it was laid out in memory. So you get the least amount of page faults, which is 128. Whereas in the first case, it's the worst case, right? So when you're doing scientific computing and stuff, you have to be aware of how this memory are laid out, and any program, right? So if you change that program from there to here, your program may not actually, your logic may not change, but you see a tremendous improvement in the number of page faults that you get, right? So so one of the people who are very aware of this fact is the scientific computing folks, right? In fact, they have to make sure that this stuff is maintained, right? And one of the harder things to do in this context is matrix multiplication, right? Hope you guys remember the matrix multiplication, right? Matrix multiplication, you have two matrices, and you go here one way, you go here one way, right? So that's guaranteed to be bad for any architecture, right? If you're row major or column major, you're good for one, you're bad for another. So if you implement it like this, right? One of this arrays would be getting 128, the other would be getting 16384, right? So they'll go through algorithms which try not to do this kind of a stuff, right? Which you don't think about it from a C perspective, but from an actual machine perspective, it's all important, right? So that's essentially what we kind of went through so far. I mean, there's a lot of little techniques we learned, and hopefully you understand what is the learned, and hopefully you understand what is the important stuff and what is, So the fact that the reference bits and all those things are incidental, what the hardware gives you, sort of what we went through on the homework project, is what I want you to get out of this module. Right? Sorry, it took a little bit. That time is actually running kind of slow. So see you guys after spring break. So if you want to take the the exam, I have the hard copy if you want.